Good evening, everyone. Welcome to the fourth discussion hour of the course on robotics and its advanced concepts. So, this week we will discuss about the kinematics of parallel robots, and that has been discussed in the week 4 lecture slides. And we will see how the kinematics of parallel robots is slightly more involved than the serial robots that we have seen till now. So I'll discuss a couple of mechanisms and I will go into detailed derivation of the kinematics of those mechanisms. In case you have any doubts anywhere in the derivation of the kinematics equations, you can stop me at that point and I will try to clarify your doubt. Okay, so let's get started. So first we should understand like what is a parallel robot, or we should be able to identify when we see a parallel mechanism. So the key how to identify is to find closed loops. So all parallel robots have closed loop of links. Right. A very most common example is the and which we'll see in today's discussion is the 4-bar mechanism. That looks something like this. So key thing to note in parallel robots is that number of joints, that is J, is greater than number of degrees of freedom. Like in this case, there are four joints. There are four joints, but only 1 degree of freedom. And why there is only 1 degree of freedom? Because if we specify one of the joints and the links are rigid, then we can exactly know the configuration of the entire mechanism. Right? So that one joint is actuated, that one joint is actuated and remaining three are passive. Right? So let's say if I put a motor on this joint, right, and if this starts rotating, then these three revolute joints would automatically start rotating in a certain manner and that we can derive by doing the kinematics of this mechanism. And the application of 4-bar mechanism is very diverse. uh, a most common configuration is the crank rocker mechanism. The crank rocker mechanism, you would have you might know, is in the engine, and it is used to convert circular motion to reciprocating motion. Right, so crank rotates entirely in a circular motion, and the rocker is basically doing a reciprocating motion. So that is used to basically drive the pistons in the IC engine, right? So that was a quick example. So key thing to note is that in parallel robots, the number of degrees of freedom is is less than the number of joints, as some of the joints are actuated and other joints are passive. Okay, now the direct or the forward kinematics of parallel robots is not as trivial as the series uh, robots, right, or serial robots. So we have to basically arrive at the same point from different different loops. Sorry, right. So what I will do now is directly go into the uh, deriving the kinematics of a parallel robot, and that is the mechanism that we were discussing towards the end of the last discussion hour. So I will just pick up from there, and that is the 3 degree of freedom parallel manipulator. Now what I would suggest here is to I will create some uh, labeled diagrams with multiple axes and all. So it would be great if you can also draw them along with me, so that you can understand in much better way. All right, so let me first draw the mechanism that we are discussing the last time, and just set up the problem. So let me annotate this diagram too. You might recall this from the lectures, but let me just reiterate what each of these, what are the components of these robots, of this mechanism. So this is the fixed base, right? And we will take it as an equilateral triangle, right? So this assumption we will use in derivation just for simplification, equilateral triangle, right? And this is the moving base, and this is also an equilateral triangle. Now this is a spherical joint, this is a prismatic joint, and this is a revolute joint. Right. Now, so we have three legs in this mechanism. This is like L1, L2, and L3. Right. This is the base point B. This is the center of the moving plate, that is P. Let me rename this as this is P, and this is moving plate. Right, so three legs, and each leg has three joints. Note that I'm saying three joints, not 3 degrees of freedom. Each leg has three joints, that is, it's an R, P, S, right? Revolute, prismatic, and spherical. So total number of joints in this system is 9. However, due to the constraints of the loops, the degrees of freedom, as we will see, is only 3, right? And generally the actuated joints are the 3 prismatic joints. Okay, so what happens is that when these prismatic joints are actuated, the length of that, the link would change, and since the two ends of those links are one side connected to a spherical joint with the moving plate and one side to the revolute joint to the fixed base, and those joints are moving passively, right? So by controlling the you know uh, how much the prismatic joint is extended or retracted, the orientation and position uh, of the moving plate can be controlled, right? So what we will do, the first step that we'll do here now is, the first step is assign frames to one of the legs, and then we'll replicate that to assign frame to the fixed base and one of the legs. Okay, and then the second would be to assign the or find the Second is to basically find the DH parameters. Third is to find the transformation matrices. Right, and fourth, that is the final objective. Final objective is to find the expression for the position and orientation of the moving plate. Find the expression for the position and orientation of the moving plate with respect to the base B. Right, so that's where we want to arrive, and we'll take this step by step process in order to arrive there. Any questions till now? Okay, so let's continue and do the first step of, and the, I would say, the most crucial step of this process is to assign the frames. Since it's not a planar mechanism, so I would draw the images from different perspectives in order to give you a better picture of how the frames are assigned, and an intuition of how things are moving. So just let me know if it is something is confusing at any point in time. Okay, let me bring this. Okay, let's continue. So first we will draw the frames. Let me just do, if I can select. Okay, I'll draw once again. No worries. So what I will do now is draw the I will draw the fixed plate, and I will draw one of the legs, such that because we can replicate that same thing across the three legs. So for better clarity, I will just draw one leg right now. So this is the fixed base, and Just one frame I will draw here itself, because it needs to be drawn in the entire mechanism. So let me draw it here. So we attach a frame at the centroid of the base, basically the fixed base, and all right. So this would be the frames of the fixed base, right? So this would be YB, this is XB, and this is ZB, right? This is the fixed frame, and it is attached to the centroid of the base plate. All right, so now here I will again draw the same base platform from a slightly different perspective. So here is the again the centroid B, here is the axis YB. From the centroid to the first joint is basically XB. Okay, now I will draw the now here is the revolute joint, right? And from here goes the prismatic joint. And here is the spherical joint. And we will mark this point as S1. Right, so our again I will write our goal. Our goal is first to find the transformation matrix from S1 to B, and that will give us the position vector from B to S1. Right, and we will repeat that process for the other two legs. Okay, so now let's get back to the frame assignments. Now the base frame is here, but as we do for any any mechanism, we assign a 0th frame that is coincident with the first frame of the robot. So we will reassign a 0 frame here, right? So whose XB is along this, and we'll mark the, so this is origin 0, right? And this will be Z0, and this will be coincident with Z1, right? And X1 would be perpendicular to Z1, but since it's attached to the link that is rotating, it's it would be in some position like this, right? So this would be x1. Now this is x1, and basically x and x2 we can draw parallel to x1, right? So this is x2, right? Now z2 is basically along this prismatic joint, so this is link 1 and this is link 2, right? There are two links only, link 1 and link 2. So z2 is the prismatic along the prismatic joint, this is z2, right? So since there are two links, we assign frames here, and since we need to find the position of the that center of the spherical joint, and spherical joint has three revolute axes intersecting at there, but we need not assign any further frames in order to find the position of the spherical joint. So uh, let's again re understand the frame assignment process. So xb and yb are the frame attached to the centroid of the base link. Then there is a frame attached at the origin of the revolute joint, coincident with the the frame that is rotating with the revolute joint. So z0 and z1 are coincident, and x1 is rotated because we are showing a non-zero revolution of the revolute joint. And now at this point I will follow the convention that has been used in the lecture slides, and the convention is that there the angle theta 1 is measured between the base plate and the first link, right? So this angle is basically written as theta 1 in the lecture slides, right? So this angle is given as theta 1. Then if I draw from, so this is, you can say, an isometric view of the mechanism. Now if I view along yb, if I directly view along yb, then it would look something like this, right? Viewing along yb means that I am viewing from this side, so directly side on position. So then it would look like this is the plate here, right? This is the revolute joint, right? uh, this is point B, this is origin 0, right? This is xb, x0, and this is x1, and z0 and z1 are coming out of the plane, right? And yeah, and this is the link, okay. So if this is theta 1, then if I draw perpendicular here, then this will be 90 minus theta 1, and this will be theta 1. So this is again 90 minus theta 1, right? Also, one more thing to add here is that this prismatic joint changes the length of this, and this will denote as L1, again going by the conventions of the lecture slides, right? So any doubt in the frame assignments, anyone? Okay, so now that we have assigned the frames, the next thing that you would do is to basically write the dh parameters for this specific leg. Okay, so since there are two links, there would be two rows in the dh parameter table. So let's make a table. I will first write the values and then we will discuss how do we arrive at them. Okay, so let's look at the first row, right? So first row means we have d0. D0 is basically the distance between uh, x0 and x1, and since x0 and x1 are intersecting, so the distance is 0. Okay, now next is ai minus 1. Ai minus 1 is the link length parameter, and that is the distance between the z0 and z1 along x0. So again, z0 and z1 are coincident at the same axis, so this is also 0. Just a second, this alpha looks a little bit awkward. Right, so I think this I confused with d. This is alpha, so I will again explain. Yeah, so the first is the link twist, that is alpha. Since z0 and z1 are coincident, so alpha 0 is 0. Then we have a0. A0 is also 0 because z0 and z1 are coincident. Then we have di. So di is basically the distance between x0 and x1. Again, x0 and x1 are intersecting, so that is also 0. Now finally we have theta, the joint variable theta I, and since we have taken this angle to be theta 1, so about the uh, about the z1 axis, the angle between x0 and x1 is given by 90 minus theta 1, right? So we are basically taking this angle in this direction about this z1 axis, right? About this z1 axis, and between the x0 and x1, right? So this is basically angle between x0 and x1 about z1, right? and that is pi by 2 minus theta 1, right? So that is the first row. Now for the second row, again we calculate the link twist. So link twist is basically now the angle between, so alpha 1 is the angle between uh, z1 and z2, right? Angle between z1 and z2, and how do we rotate in order to get from z1 to z2, right? So if you see, this is z1, this is z2, and I have to rotate about x1 in order to get from z1 to z2. And since x1 is in this direction, if you rotate about this direction, then if you rotate, you have to rotate about the opposite of this direction, right? By pi by 2 in order to get from z1 to z2, right? So we basically have to rotate like this, like rotate like this in order to go from z1 to z2. So the angle is minus pi by 2, right? Is this clear? Because last time we were deriving this and there were some confusions regarding this. So please let me know if there is still some doubt at this point. Yeah, sure, Ninath. So basically, to be consistent with the the notation and the axis assignment and the angles that has been taken in the lecture slides, I am sticking with that. So in this lecture slide, theta 1 is the angle between the base platform and link 1 on the inner side, right? So this is the base platform, this is link 1, and this is the theta 1 value that is shown in the lecture slides. Now for the DH parameter table, I have to get, so theta 1, if you remember how theta 1 is defined. Theta 1 is defined as the angle between x0 and x1 about the z1 axis, right? So that would be the definition of theta 1, right? And here now in this side view image that I have drawn, you can see that the angle between x0 and x1 about z1 is 90 minus theta 1, right? So that's why we keep the value here 90 minus theta 1. If let's say in a different notation I keep this angle itself as theta 1, then here theta 1 would come. But since here this measurement is taken as theta 1, so to be consistent, the angle, the joint variable angle for this convention would come out to be 90 minus theta 1. Is it clear now? No, 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 no. Zeroth is not for the revolute. So zeroth frame is basically the frame that we assign at the base of the kinematic tree in any any mechanism that we analyze, right? So if you remember, let's say for a 2R manipulator system, right? For a 2R manipulator system, this is the 2R manipulator system, right? There's a joint here, there's a joint here, right? So we assign a frame at the starting, right? That is aligned to the wherever my this could be my world frame, right? This is my frame that is aligned to the world frame, but at coincident with the first joint, right? This is the first joint, and then the frame that is coincident with the first link is assigned like this, that is frame 1, right? And this angle is theta 1, right? This is, so the same thing we are doing here. This B is our equivalent to our world frame. It is fixed and attached to the centroid of the base platform. Then we attached another frame here that is coincident with the revolute joint, the first revolute joint, right? And that is frame 0. And then frame 1 is the frame that is fixed to link 1 and rotates with link 1. And frame 2 is for the prismatic joint, right? Frame 2 is for the prismatic joint. which basically moves as the prismatic joint moves. Again, is this clear now? Okay, that's great. So, yeah, so moving on. So, we have the DH parameters. So, we have the DH parameters for link 1, right? Now, let me just erase this. Okay, now what you can do, so first thing is that the same thing can be applicable for uh, for other two links as well, because it's the same thing, just uh, you know for two links that are arranged symmetrically about the centroid of that equilateral triangle. So this is the equilateral triangle, one is here, another is here, another is here. So the DH parameter table would be the same. What would differ is how we transform from this 0th point to the B point, right? So let me just again draw a top view diagram of just a base platform. you know so this is where the B is here, our world frame, right? At each corner we assign local worlds, you can imagine. So this is uh, origin 0 for the, or I think we should do better. Okay, origin 0, this is origin 1, right? And this is origin 2, right? And this is basically, this is at 0 degree, right? And for this we have rotation about 120 degrees about ZB, right? And here we have rotation of 240 degrees about ZB, right? So basically we have the same thing up to up from the spherical S1, right? From this point to this point, from the point at the spherical joint to the point at the revolute joint, all the transformations are same for all three legs, right? So let me be consistent with the namings. I will mark this also as 0 then. Okay, so note that, and this you should like be convinced that since all three legs are identical, between this point and this point all three legs are identical because they have the same geometrical structures and same joints, right? So note that the transformation from SI, that is the point on the spherical joint, to OI, basically the point on the revolute joint, right, is exactly the same for all three legs, right? What changes what changes is the transformation from OI to B, right? So like the transformation from O0 to B is different than O1 to B and then O2 to B, because these, there is an added rotation for these two. Okay, so the transformation from Si to Oi is the same for all three legs, and what changes is the transformation from Oi to the base frame, right? So first we'll now do the, now we are at the, so if you look at the steps, so we assigned the frames and we found out the DH parameters, right? So two steps are done, right? Now we are at the third step. Now we are at the third step, that is find the transformation matrices. Okay, so what kind of transformation matrices do we need to find, right? So in this, we have to first transform from frame 2 to frame 1, then frame 1 to frame 0, and then frame 0 to frame B, right? So we will do for leg 1 first, right? So that is, we'll transform from frame 2 to frame 1, then frame 1 to frame 0, and then frame 0 to frame B. And this is given by T2 to 1, then T one to 0, and then T 0 to base, right? So this final thing of expressing 2 in terms of the base, right? So this, if you can, yeah, so this thing, base top, yeah, so 2 to 1, 1 to 0, 0 to base would be the order, right? So it would be T 2 to 1, then T 1 to 0, and then T 0 to base, right? Now what you have to do is we have to find each of these matrices. So let's do that. So first let's find this part, right? This part which is equivalent, we can write T from 2 to 0, right? So T from 2 to 0 is and that is, so for 1 to 0, for 1 to 0 we have rotation about the z axis by an angle of pi by 2 minus theta 1, right? So just as an aside, cos 90 minus theta 1 would give sine theta 1 and sine 90 minus theta 1 would give cos theta 1. Right, so I will directly write the expression here. So here we have cos theta 1, so that will become s1, this will become minus c1, this will be c1, this will be s1, and then 0 0 0 1, then 0 0 0, and then there is no translation between those two frames, so this will all be 0 and 1. Right, now for the second joint we have the we have link twist. So link twist is about the x-axis, right, and that is of minus pi by 2, and we have about the z-axis we have L1 displacement, right. So first rotation part would be, right, so let me just, so this part is rotation about z1 by an angle 90 minus theta 1, right, and then here what I will write is 1 0 0 0 0 0 1 minus 1 0 0 0 0 1 L1 0 0. Okay, so what is this? This is the rotation matrix corresponding to twist angle. So this is R about, right, so R about alpha 1, sorry, x1, rotation about x1 by an angle of minus pi by 2, right, and this part is translation along z z2 by a distance L1, right, so this is, as you would see, translation along z2 by a distance L1, right. So let's multiply these two. Any doubts here? Because understanding this is important, because this process will be repeated. Okay, so let's do the multiplication. So all right, let's multiply. So first row, first column, this would be S1 S1, first row, first column, first row, second column. Yeah, because we don't have we are trying to find the transformation up to this point itself, right. So the frame that we are trying to describe with respect to base is attached at the center of the spherical joint itself. So we, we are not, right now we are not describing the frame directly, the frame attached to the center of the, let's say, the plate here, right. So yeah, the spherical joint does not come into the picture. So yeah, continue with the multiplying. Please multiply on your own also and verify, because there could be some sign mistakes here and there. So S1 0 0 0 0 0 0 0 0, this would be 0, and then it would be 0 minus C1 0 0, and then here it would be 0 0 0. Mm. Wait. This would be L1 would be round Z. X1 Z1 Z2. And here this is about Z1. So let me just check. 2 to 1 and 1 to L1 is given by this. Let me just check. This angle is not correct. Yeah, this would be incorrect. And yeah, L1 S1. Yeah, so here it is taken about the Y. I also do this change. Okay. So basically what we have is, this is X1, this is Z1, so this is about Y1. Okay. So because Z cross X. Yeah, so what the convention that has been used to take the direction of L1 is that, please note in this figure that this is X1, this is Z1, and the y-axis is basically Z1 cross X1. So this is the Y1 axis, and L1 is along this axis. Okay, so we should keep L1 here, and we can continue with the multiplication. So this would be minus L1 C1, right? And then in the subsequent row, let's move fast now. So C1 0, it will be C1, and then 0 0 0, and then 0, and then S1, right? And here it would be L1 S1, right? Third row would be 0, then again 0 0, minus 1, right? Third row would be 0 0 minus 1, third row, first column 0 0 0 0 0 0, minus 1 0, that is fine, and then 0 0 0 0, this is gone, and then final would be 0 0 and 0, right? And finally it would be 0 0 0 1. Okay, so this is the transformation from the point at the spherical joint to point at the revolute joint, right? This is the transformation. Now the other part that we have is transformation from 0 to B, right? Now 0 to B is basically, we'll have to again refer here. So what we want to do is basically we want to transform this B frame to the 0 frame. Okay, so first thing that, so here what we want to do is transform B to 0 frame, right? So this involves two things. This involves translate by B, where B is the, B is this distance, this is B, right? So since this is an equilateral triangle, this is the same, right? B. So translate by B and then rotate about, right? So imagine once I translate by B, this frame comes here, right? But still the ZB is pointing upwards and we want to make it point coincident with Z0. So to make ZB coincident with Z0, we have to rotate about the X0 about 90 degrees, right? So rotate about X0 by pi by 2. Okay, so translate by B, and that is along X0, and rotate about X0 by pi by 2. Again, let me just make it clear. So what we are doing is, this is the frame, B frame, ZB, YB, XB. We first translate from this point to this point. This is the distance B, and we translate and come here, and then about X0 I rotate by 90 degrees so that ZB is aligned with Z0 and YB is aligned with Y0. Okay, any doubts in this? So we have to write the transformation matrix. So first rotation about this will be cos 9, this will be 1 0 0 0 0 since it's about x-axis, right? And this is uh, the translation is about the b, the translation b is about the x, so this is that, and this is cos 90, so 0 sine minus 1 and sine 91 and cos 90 0, right? So this is the transformation basically. Any doubts in this? Right, so this transformation is between which two frames? The frame here at the base of the revolute joint, that is the 0th frame, and the frame at the centroid of the base platform, that is the world frame. So this is the transformation. So finally what we want to write is basically b to 2, right? And that is given by b to 0 and 0 to 2, right? So let's multiply these two and write the final thing. Okay, so again multiplying very carefully, what we have is first row first column, so that is s1, then first row second column is minus c1, and first row third column is 0, and first row and first row and fourth column is first row and fourth column. Okay, which I am multiplying incorrectly, I believe. Let me just write them once again. So b t2 is equal to, first write b0, so that is 1 0 0 0 0 minus 1 0 1 0 0 0 0 1 0 0 b, and here it is s1 0 minus c1 c1 0 s1. Yes, so now we have to multiply. So first row first column would give s1, first row second column would give 0, first row third column would give minus c1, and this would give b minus l1 c1, right? Now second row would give 0, then 0 0 1, and then 0 0 0, and this would be 0 0 0. This would be c1, this would be 0, this would be s1 most likely. Let me check. C1, yeah, and this would be L1 S1, and finally it would be 0 0 0 1, right? And this is basically the, so this is the position vector. This is the position vector to from B, right? And that is B minus L1 C1 0 L1 S1, right? This is the position vector. Note that the y coordinate is 0 because we have chosen frames such that, the we have chosen the x-axis to be like crossing through the first joint. So the y coordinate is 0 in this configuration for this leg, for the first leg, right? So this is the position vector for the first leg. So this is the position of the center of the spherical joint of the first leg from the centroid of the base platform. And like, if you want to intuitively, just do a quick sanity check about this result, you can quickly draw us again a side view where this is a side view where this is B, this distance is B, right? And you have this link L1, you have this link L1, right? And you want to know the position in this frame, right? In this frame. So how will you calculate this position? So if this is L1, this is theta 1, right? So then this distance is basically L1 C1, and this vertical distance is basically L1 S1, and that's what we have got, right? This remaining distance is the one coordinate, so that is B minus L1 C1, and in this direction this is the coordinate. So in Z1 it is L1 S1, and Y is 0 because it's lying on the x-axis itself, right? So this quick check helps us be confident that whatever process that we have followed, that is giving us sensible results. Any questions here? This is the quick check. Okay, now what we do is basically for the other two links as well. As I mentioned, the transformation from this point to this point is the same, and what changes is that we have an additional rotation there, right? So transformation from 0 to B is also the same, right? That we have to translate by B and then rotate 90 degrees about the x-axis. Thus, the one thing that changes from this case, the leg 1 that we just saw, and this leg 2 and leg 3, is that in leg 1's case, the z-axis, there was no rotation about the z-axis of the base frame, but in the second case and third case, there is a rotation about of 120 degree about the z-axis and a rotation of 240 degrees about the z-axis, right? So what we have to just do is while calculating 0 to B, while calculating 0 to b, we have to add one more rotation matrix, one more transformation matrix that accounts for that rotation, right? So let me just quickly write those rotation matrices for leg 2 and leg 3, right? So what observation we have is that for leg 2 and leg 3 we have an additional rotation. Let me continue here. So for leg 2 and leg 3 we have an additional rotation about ZB of theta 2 is equal to, let me not use theta 2, of 120 degrees and 240 degrees, right? So for leg 2, this t base to 0, that involves the usual t base to 0, right? So it involves one additional RZB of 120 degrees, and then rest is the same, that is the transformation that we did for leg 1, right? Now this 120 degree rotation about the z axis, so cos 120 is minus 1 by 2, 0, no, not 0, sine 120 is root 3 by 2, root 3 by 2, 0, then this is, so cos theta minus sine theta, right? And then sine theta and cos theta, right? And 0, 0, 0, 1, 0, 0, 0, 1, and there is translation and all have been already accounted for in this part, so we need not go there. And the other matrix was, let me just see from here, it was this, right? 100B, so 100B, then 00 minus 10, then 0 0 minus 1 0, then we have 0 1 0 0, 0 1 0 0, and we have 0 0 1, right? So now let's multiply these two. Okay, so first row, first column, that is minus 1 by 2, then first row, second column, that is 0, first row, third column is root 3 by 2, and first row, that is minus b by 2, right? Then we have second row, that is root 3 by 2. Then we have 0, then we have half, then we have root 3b by 2, right? Third row we have 0, 0, 1, 0, and we have 0, 0, 1, right? So this is the transformation from base to 0 for that particular leg. And similarly for leg 3, it's the same process, exactly same process, right? Just that we now have RZB and a rotation of 240 degrees, right? And the same thing, that is B0 T leg 1, right? And I will directly write the final matrix. So that would be, in this case, that would be uh, 1 by 2, 0, minus root 3 by 2, minus root 3 by 2, 0, 1 by just a second here, second row, third column. Okay. So this would be cos theta is half in that case, so that would be half into minus, so minus half. Please check this multiplication on your own also, because I'm trying to wrap it up soon. And this will be like minus b by 2, and it's in third quadrant, so cos and sine both are negative. Cos and sine both are negative. Okay, so this would be also this, right? Cos and sine both are negative. This would be plus, I believe. And this would be root 3 minus root 3 b by 2. Okay, so yeah, basically you get the idea, right? Yeah, these notes are being shared on a drive link, like that link has been shared on the course website also. So these notes are, every week's notes are being updated there. All right. So now we have the transformation for the other legs also. Okay, and if you multiply these transformation from 0 to b to the transformation that is the same for all three, that is this one, 0 to 2, right? So finally what you will get, right? So by multiplying the individual b2 with this for leg 2 and 3, we get position of S1 and S2, right? So if you remember, we are interested in finding the position of these three spherical joints, that is S0, S0, S1 and S2, right? So this is S0, this is S1 and this is S2, right? So now by doing this entire process, we have the position of S0, S1 and S2, right? So position of S0 in base frame B, that is B minus L1 C1 0 L1 S1, then B, then this is S1, and this is minus B by 2 plus L2 by 2. So this is the column of the transformation matrix that you finally get, last column. So that last step, I have done the entire thing. This last step you can do the calculation for the other two legs and just verify with this result. And if there are any discrepancies, we can discuss. And finally, we have minus b by 2 plus half L3C3 minus root 3 by 2 b plus root 3 by 2 L3C3 and L3S3, right? So we have these 3 points, right? And now finally what we have to do, so what we have right now is we have these 3 points, PS0, PS1 and PS2, right? And we have taken this as an equilateral triangle, right? So this is A, this is A, and this is A. Now we get 3 relations. We can get 3 relations. That is the distance between, so by subtracting the position vectors, we get the length of the side, right? And we know the length of the side. So if we do PS0 minus PS1, the norm is, Euclidean norm is A. Then similarly for PS1, PS2, the Euclidean norm is A. And finally PS2 minus PS0, the Euclidean norm is A, right? So we have 3 equations. These 3 equations we have, right? And if you see in these in these expressions, what unknowns do we have, right? So L1, L2, L3, they are the joint variables, right? So they are the inputs basically. And apart from that, we have theta 1, theta 2, and theta 3, right? Which we can calculate. So three unknowns. We have three unknowns. Okay, so we can basically once we know L1, L2, L3, our inputs, we can calculate the three unknowns. Right, so that is what is being described here also in the lectures. Right, so this is basically the three equations that I just described, right? We can also put squares here, so like this. Okay, so that three equations and three passive variables that we can calculate. So the process of how to calculate that is described here. Okay, and we can get those values. Now finally, the position and orientation of the moving platform, right? So position and orientation of the moving platform, because we are interested in the centroid, so we can use the formula of centroid of a triangle, that is the average of the coordinates of the vertices. So we know the position vectors of the vertices, and by taking the average we can calculate the position vector of the centroid, right? And similarly, since we know the 3 points on a plane, we can calculate by doing the position vector. We can calculate the orientation of the platform by taking the cross product of any two edges of the basically the any two edges of the triangle, right? So like this we get the position and orientation of the moving platform, right? So if what we're interested was this, so P is basically given as 1 by 3 of PS0 plus PS1 plus PS2, right? This is the position of the centroid of the moving platform, right? And the orientation is given by cross product of any of the two edges, right? That is the orientation. Any questions and doubts here? RS and PS, are you talking about? I'm not exactly sure which slide are you talking about.
Hello.
Yeah, which slide are you talking about?
Yes. Sorry, I couldn't speak before this. The one before this one.
This one?
Yeah, these are all the coefficients, right?
Yeah, I think so. The polynomials that we want to find out, the quotients of those polynomials.
Oh, okay. Got
Yeah.
it. Okay, thank you.
Yeah. So basically, yeah.
Back. So we found out the orientation. That's good. Um, yes, I think I'm good. I'll check on the calculations. I didn't get a chance for that, but otherwise I understood. Thank you.
Yeah, so once we get the position vector of the three vertices of a triangle, we
Mm-hmm.
can very well calculate the position of the centroid by taking uh, the average of those three vectors, and
Mm.
the orientation we are calculating basically by, so we want to calculate, so basically think of this as a plane, and we want to calculate the normal of the plane, because the normal of the plane gives us the orientation of the plane, right?
Yes.
So we have, let's say we want to take one direction this side, one direction, uh, sorry, one direction this side, right? So this would be edge 1 and this is edge 2, right? So these are two vectors, and when we take cross
Yes.
product of these two vectors, we would get a vector that is perpendicular to these two, right? This is
Okay,
perpendicular to
got it.
these two. So that's how we get the
Got it.
normal to the plane, right? So if I draw in this orientation, okay, so this is, okay, sorry, let me draw it in a better way. Oops. This is P, yeah, this P, and the orientation, right? So this is, edge 1, this is 2, and this is the orientation, right? So this is the normal, this is the normal, and n is basically, and if we,
Normal to the.
yeah, so n is basically v1 cross v2, okay,
Yeah.
and the
Okay.
unit vector you can also find out by doing v1 cross v2 and by the norm of that. So this is the normal to the moving platform, and once you know the normal, you know the orientation.
Okay, got it. Got it. Okay. Okay. That transformation, like you said, remains the same, like from the base to the zeroth and zeroth to the first. So zeroth is just orienting the revolute joint with respect to the base, and then 0 to 1, and then okay.
Yeah, so basically from the revolute to the spherical, right? So that
Mm-hmm.
remains the same for all three legs. Okay, what changes is that the transformation from this zeroth to the base, and that also is different in just one aspect, is that in the other two legs we are also rotating about the z axis by 120
Hmm.
degrees and 240 degrees.
Understood. Okay.
Yeah.
Um, And okay, yeah. I guess I have a doubt with respect to week 4, but then should I bring it up now or
Week 4, in that would be like, about which mechanism is this mechanism or some other doubt?
no, inverse kinematics of Stewart platform, Stewart platform again. So the same mechanism,
Mm-hmm.
but I think instead of the revolute there is universal, and then my doubt is with respect to a specific slide
Okay. I
when we
think
had
I would
yeah
need to have a look at that before, so maybe we can discuss it in the next discussion hour if it
next
is
one.
not exactly related to some
No,
assignments
no,
and
no,
all.
it's not related to. So this is so you're discussing with respect to week 3 assignment, right?
Yeah, I mean week 3
Okay,
and
okay.
somewhat like, uh, I think week 4 has parallel things also. It has the, I think it has questions around orientation of this platform itself, I think.
Right. And one final question, it's a general knowledge thing, I didn't know. But at the end of everything, would the workings of the assignment questions be shared by any chance?
Uh, I would
Like
need,
at the towards the end of the, like, as the exam
ha
nears,
ha ha ha
not
ha. That exactly I'm not sure about. I would need to consult, maybe you can write to the instructor if
Okay,
that's
yes, yes.
possible.
I will. Okay, okay. Yeah, I think. Thank you, thank you. This
Okay.
was good. Thank you.
Okay, so in case there are no other questions, we would stop at this point, and I again encourage all of you to go through this entire process for each of the legs on your own, right from the assignment of TH parameters to the final calculation of the position vector of the uh, base moving platform and the orientation. So that would help reinforce the entire process and maybe clarify some of the doubts that might not have come up while I was describing the process. So, okay, guys, I will wrap up here, and next week we will continue with the applications of parallel robots.
Okay, yeah.
Okay,
Thank you.
thank you.
Thank you.
Goodbye.
Oh, Amritanshu,
Yeah.
one last thing was next week, would you be able to discuss one of the, so I'm just like one of the week 4 assignment questions as one numerical. So the deadline is 19.
Okay.
So I think it would have passed definitely.
Uh-huh.
Just the working of assignment question, which is 5th question and the 9th. So 2 numericals.
Okay, let me just note them down. Question 5 and
Question 8.
question 8.
There are only 2 numericals in the assignment. Yeah, yeah.
Okay, okay. I'll have a look at them.
Okay.
No worries. Yeah.
And thank you for resolving my previous doubt, like last week's doubt about pi by 2 minus theta 1.
Yeah, yeah. It's good that it was cleared.
Thank you.
Okay, goodbye.